A 7 million parameter model, small enough to run on a laptop, reportedly beats Gemini 2.5 Pro and DeepSeek-R1 on a benchmark specifically designed to resist pattern matching. That's the headline claim behind tiny recursive models. I cloned the actual code, installed the actual dependencies, instantiated the actual architecture, and dug up an independent replication that stress-tested the claim. Here's what's real, what's oversold, and what's genuinely clever. The pitch, from author Alexia Jolicoeur-Martineau at Samsung SAIL Montreal. A 7 million parameter network, trained entirely from scratch, no pre-training, no internet scale corpus, reaches 45% on ARC-AGI 1, 8% on ARC-AGI 2, and around 87% on Sudoku Extreme. The thesis is direct. For narrow, structured reasoning tasks, recursively refining an answer in latent space can beat throwing more parameters at the problem. Mechanically, here's what's happening. The model holds a current answer, y, and a latent reasoning state, c. On each cycle, it updates z several times conditioned on the question and current answer, then uses that updated z to refine y. This repeats up to 16 times, with a learned halting head deciding when to stop. Critically, none of this reasoning is ever written out as text. Unlike chain of thought prompting, it happens entirely inside a continuous latent vector. This part matters to me, so I actually did it instead of trusting the abstract. I cloned the real repository, installed the real dependencies, and instantiated the exact architecture class from the paper's own code, using the Sudoku configuration from their README. Parameter count came back at 6.83 million, matching their 7 million claim almost exactly. I then ran an actual forward pass, and a recursive loop executed correctly, producing properly shaped output logits. I hit one real bug along the way, a puzzle embedding dimension mismatch, fixed it, and confirmed the mechanism genuinely works as described. What I could not do is fully train it. The smallest experiment needs a GPU for 18 to 20 hours, hardware I don't have in this environment. Here's the part that should genuinely change how you read the headline number. A separate research team, publishing independently, obtained the official ARC prize verification checkpoint and reran it under controlled conditions. The official 40% score depends on 1,000 sampled task time vote, drop that down to a single pass, and it falls to 29.25%. But the real finding is this last row. When they blanked out the puzzle's identity token, the same input grids, the same weights, just no correct ID, accuracy didn't drop. It collapsed completely to 0. 3 findings worth sitting with. First, the puzzle ID dependency suggests the model behaves less like general reasoning and more like a lookup key retrieving a task-specific program. Real accuracy on genuinely unlabeled new tasks is an open question, not a demonstrated strength. Second, a recursion depth analysis found that 94.4% of the model's final accuracy is already present after just the first reasoning step, out of a possible 16, so the celebrated deep recursion mostly isn't doing much work at inference time. Third, in fairness, when the same team fine-tuned a plain Llama 3 8 billion model with no special tricks, it scored only 2.15%, so TRM's efficiency advantage over a naive large model baseline is real and worth taking seriously. On raw efficiency, measured by that same independent team on identical hardware, TRM is genuinely impressive, over 100 times the throughput of a fine-tuned Llama 3 8 billion, a fraction of the memory. If your task is narrow and well-defined, like the ones TRM was built for, that efficiency argument holds up under real scrutiny, not just the paper's own numbers. Be precise about scope. This is built for narrow, structured, grid-shaped puzzles from a fixed, known task family, Sudoku, mazes, IRC-style grids, not general reasoning, not language understanding, not open-ended problem-solving of any kind. The comparisons to Gemini or DeepSeek are real numbers on one specific narrow benchmark, not evidence this replaces a general reasoning model at anything else. Where this genuinely shines is as a research direction into efficient, purpose-built architectures, not as a general tool you'd reach for. Practically, 3 things to know before you'd build on this. The GitHub repository has been archived and made read-only by its own maintainer, citing limited capacity to keep maintaining it, so don't expect further updates. No pre-trained checkpoints ship in the main repo. Training from scratch needs 18 to 20 plus GPU hours even for the smallest task. And on the positive side, An independent team has already replicated and stress-tested it, which is genuinely more scrutiny than most trending repos ever receive. My rating. Technically, this is a genuinely clever, well-engineered piece of architecture research. The parameter count checks out, the efficiency numbers check out, and it does something real with very little compute. Where it loses points is the gap between the marketing framing, beats Gemini 2.5 Pro, and what independent replication actually found. A narrow benchmark result propped up by puzzle identity lookup and heavy test time voting, with shallow effective recursion underneath. I'd call it a 7 out of 10. Strong research. Oversold headline. That's tiny recursive models, verified hands-on, and checked against independent replication rather than just the abstract. Worth studying if you care about efficient architectures, worth being skeptical of if you saw the headline comparison to Gemini and nothing else. Links in the description, along with the independent critique paper. See you in the next one.